I'm David. I'm one of the lecturers in the Maths Learning Centre here at Uni of Adelaide, and this is a rough and ready lecture on optimisation problems with calculus. This is the third in a series of lectures on using calculus. In the first two, I showed how I could use calculus to figure out the shapes of graphs of functions. And now I'm going to use those same techniques to figure out how to solve problems where you're trying to find the maximum and minimum of things. To solve optimization problems, which means finding the maximums and minimums. Now, just to point out, I spell it maximums. I think the English language has moved forward to allow that, but some people do the plural as maxima and minima. Maxima is a plural. The singular is maximum. So please don't say at any point that you have found a maxima. That's grammatically incorrect. You can say you've found a maximum, you can say you've found two maxima or two maximums, and that's fine. Okay, so that's the grammar lesson over. So I'm going to need to talk about something to do with functions that I didn't mention before. And to do it, I'm just going to jump over here to the computer. And here is a graph of a function. It's a pretty wickedly wiggly function. In the previous lectures, I showed how to use calculus to find turning points of this function. So if you knew what the formula for this was, you could use derivatives. But you can already see, even without calculus, that it's going up, and then it's coming down, and then it's going up, and then it's coming down. It goes up a bit, and then it's going down. And so this function, the highest it possibly gets is here. That's what a maximum is. A maximum is the highest value that something has. So the highest possible y value that happens is there at about 7.613, according to the graph. But there are some other places. Places that are also high. This here at 5 is the highest y value, at least nearby. So if I zoom into this bit here, then this is the highest y value in this view window. It's higher than all than the y values that are around it, and that's called a local maximum. Similarly, if I go over here, this is a local maximum as well. When I zoom in this far, it's the highest y value in the view window. So that's called a local maximum. And this over here is also a local maximum. It's higher than any y value around it, but it's also higher than any y value anywhere. So it's called a global maximum. So functions have various little peaks and troughs, and each of the peaks is called a local maximum. And one of those local maximums is going to be a global maximum. And similarly, this is a local minimum, because when I zoom in, it's the lowest y value there. And this is also a local minimum, since if I zoom in far enough, it's the lowest value there. But no other places are going to be local maximums or minimums, because this point here, no matter how far I zoom in, there's always y values higher than it and y values lower than it. Now this graph technically doesn't have any minimum at all, because if I keep zooming out, it just keeps going down and down and down and down. So it has no minimum at all. However, if I was only looking at just this bit here, I just did a little magic there. If I was only looking at this part here, this green bit just here, then if I'm only looking just inside this green bit, there is a local maximum here. And, well, it doesn't sort of have any turning points in here. So the minimum would be there at the end here. And if I was looking at this whole zone just here, then there'd be a local maximum here, a local minimum here, a local maximum here, a local minimum here, a local maximum here. And then it doesn't get below the x-axis, so the minimum is 0. And that's the idea that we're going to get at. So I'm just going to write some of that down. So just firstly, turning points of functions and maximums and minimums for functions. For functions, a turning point of a function is a local minimum if, well, in an interval around it, it's the lowest point. So it has the lowest function value. That's what minimum means. And a turning point a function is a local maximum if in some interval around it, doesn't matter how small it has to be as long as there is one, it has the highest function value. And, okay, we'll deal with that in a second. And you can, and then a global maximum and a global minimum is the function value that is the highest. So, global meaning, you know, the literal meaning of global is around the globe, as in talking about the whole Earth. But in this sense, it's just across the entire of all of the options. So a global maximum for a function defined on an interval is the highest function value. Okay. And a global minimum is the lowest function value. I'm just going to call the function f of x highest function value for all x in the interval. So what I'm doing here is writing some mathematical definitions of these things, because definitions are important to mathematicians. A global minimum for a function f of x defined on an interval is the lowest function value for all x in the interval. So the idea of a local minimum is that if you make your interval small enough, then it will be a global minimum for that interval. And I realise that I've been a bit sad, but I've done minimum, maximum, and then maximum, minimum. Sorry about that. Okay, so that's the difference. A local maximum is just higher than the points around it. A global maximum is higher than any point at all. And I just want to make one more point about that when I go back to this thing here. So as this interval, this point is the global maximum because it's higher than all of these points. And even though the function comes back up again, this point is still higher than all of these. And even though the function comes back up again, this point is still higher than all of these. So just because the function goes down and then comes back up again, it doesn't mean that that thing isn't the global maximum. That height is the global maximum because it's literally higher than everything. And what we've noticed is that the global maximum either happens at a turning point or it happens at one of the endpoints. So if your function is only this wide, only uses this part of the graph, then the global minimum is here, because that's the lowest point in this zone, and that's the highest point in that zone, so that's the global maximum. Actually, just let me do something. I'm literally going to turn off the graph outside this zone so it's a little easier to see what's going on. So this graph, which only exists inside this zone, has a global minimum here and a global maximum there. But if it existed inside this zone, it has a global minimum here and its global maximum is right at the end there because it doesn't get any higher than that, and that's the highest it can go. So that's not technically a turning point because there's no other side for it to go down again. And if I was thinking about this function beyond the zone I'm in, it doesn't actually turn there. Whereas this function, the global minimum is here because it's lower than that minimum there. All right? So when we're looking at a function on an interval, we're going to need to look closely at the endpoints of that interval. And I might do that for an example for a specific function in just a moment. Before I do that, I want to remind you about how to find turning points. Turning points happen if your function has a derivative, then turning points will happen when the derivative switches between positive and negative. Okay, so when it switches between increasing and decreasing. So just a reminder. Actually, no, before that, let me write down the other thing I said. The other thing I said that a maximum or a local maximum or minimum, or the global maximum minimum, will have to happen at a turning point or at an end point. So this is like a theorem, really. The global maximum or minimum of a function occurs at either a turning point or a point or an end point of the interval it's defined on. So the global maximum or minimum of a function occurs at either a turning point or at an end point of the interval where the function is defined. And of course, turning points, which is what I was about to say before I said this, turning points are are either local maximums or local minimums depending on whether it's increasing or decreasing on either side. Turning point only occurs when it changes from increasing to decreasing or vice versa. So remember, if a function has a derivative, let's call the function f of x, has a derivative, then a turning point will have f dash x greater than 0 on one side and f dash x less than 0 on the other. Okay. And even better, we can tell even better what's going on with that. If it's got a negative derivative on the left and a positive derivative on the right, it's got to be a minimum, a local minimum. And if it's got a positive derivative on the left and negative derivative on the right, it's got to be a local maximum. So, in this case, if f of f dash x is negative for x less than a, and f dash x is positive for x greater than a, then there is a local minimum at a. So that looks like this. There's a, and this is a sign diagram. For f dash x. And if it's negative on this side and positive on this side, then that means my function's coming down on this side and going up on this side, so it must be a local minimum. And if f dash x is greater than 0 for x less than a, and f dash x is less than 0 for x greater than a, then there is a local maximum at a. And the sign diagram will look like this. So I'll put the x's at the bottom, and here's the point A. It's going plus and minus, and technically the point A isn't the maximum. It's just a location where there is a maximum. So if the slope is positive, it must be going up here. And if the slope is negative, it must be going down here. And so it must be a maximum if it goes that way. Okay, so they're the ideas of what's going on with these functions. And I'm just going to do a quick example of one just to show you how it works. Give me just a second to get that ready. All right, I've got it ready now. All right, so here's an example. Find the local maximums and minimums for f of x, which is going to be x squared, x take 1, x take 3, on the interval from -1 to 3. From the global maximum and minimum. Okay. So I just want to point something out. I could go to a machine, could go to Desmos, and I could get it to draw it, and I could get I could look at it, and I could get Desmos to help me figure out what that maximum is. And I could even sketch this myself and draw it. But one of the whole points of using derivatives is so that you don't have to draw it, that you have the power to figure this out yourself without even really knowing exactly what the graph looks like. So if I wanted to draw this entire graph, I would normally find its x-intercepts and various other bits and pieces, but I don't have to find all of those things in order to answer the question I'm trying to answer. I don't have to draw it to know where its maximums and minimums are. So I can just figure some things out. I am going to need to know when it's increasing and decreasing, or I'm not going to be able to find the turning points, because I know the turning points are where the maximums and minimums happen. I'm going to have to do that, but everything else I can just do. So let's see. F of x is x squared, x take 1, x takes 3. F dashed x. All right, well, I can use the product rule. Product rule usually does two things at once, so I need to do like the derivative of the x squared and keep the other bit. And then I need to keep the x squared and do the derivative of this bit. And the derivative of that bit would be, well, I could do the product rule again. I'll differentiate the x take 1 and keep the x take 3. And then I'll keep the x take 1 and differentiate 3, the x take 3. Okay. Well, everything here I can see has an x in it. So actually, just let me do a little bit more. This would be 2x take 4 there. Okay, that's cool. And so everything has an x, so I will take that out. And actually there's a 2 in this one as well, so I'll take a 2x out. So I'm left with x take 1, x take 3, plus x take 2. All right. Factorising, it's useful if I'm going to try and figure out where it's 0, because finding where it's 0 is going to allow me to figure out where it's positive and negative. So that'll be 2x. Only option I have is to expand this out, I think. So x squared minus 1x minus 3x plus minus 1 times 3, minus 3 is plus 3. Plus x squared minus 2x. So I've got 2x squared minus 6x plus 3, which does not look fun to factorise. So it looks like I'm going to have to use the quadratic formula. No, can't be bothered. Quadratic formula it is. So what we want to do is we want to solve for when f dashed x equals 0 so that we can find the turning points. 6x plus 3 equals 0. So either x is 0 from here, or 2x squared minus 6x plus 3 is 0. So if I call this a, and this number b, and this number c, then I can go x equals minus b plus or minus b squared minus 4 times a times c over 2a. All right, which is 6 plus or minus, interesting. Well, that's 4 times 6, and that's 6 times 6. If you don't mind, I'm just going to do that. So that's 6, that then comes out to 2 times 6. Okay, don't think that's going to get much better, really. Hey, 2 times 6 is the same as 4 times 3. so that's, which means I can square root the 4, and I can divide everything. I can divide the top of the fraction and the bottom of the fraction by 2. Okay, well, that's what it is. I'm just going to get some approximate answers there. So 3 minus the square root of 3 divided by 2, 0.634, and 3 plus the square root of 3 divided by 2. Okay. Okay, so I've got 3 places where the derivative is 0, and I can write those down. In a sign diagram. Okay, so let's see, the options for x. Now I would normally put an arrow there, but it doesn't go on forever actually. I was only allowed to use the x's between -1 and 3. So let's pop them in, -1 and 3. So these are x's, this is going to be f of x, f dashed x. So there's a 0 here at 0. There's 1 at 0.634. And there's 1 at 2.367, which was actually 3 plus root 3 on 2. Okay, and I'm going to need to figure out where it's positive and negative. So f dashed of -1/2, I guess, in here, that's a number in there, would be, where's my calculation? It's up here. 2 times -1/2 times 2 times -1/2 squared minus 6 times -1/2 plus 3. Do you know what? -1/2, and we'll store that in x, and then we'll go 2 times x times 2 times x squared minus 6 times x plus 3 minus 6.5. Negative. Well, I guess we could do half because it's 0.6 here. So what if I put half? I store that. Oh, it went into y. Okay, that's store that in x. Okay. And I go back up here. Oh, I thought I could keep it. So 2 times x. Just a second, let me just check what x is. Yeah. 2 times x times 2 times x squared minus 6 times x. 0.5. Positive. Something between these two is 3, is 1, I guess. That I can do. 2 times 1, 2 times 1 squared minus 6 times 1 plus 3. And so we have 5 minus 6, that's going to be negative. And then over here, f dashed of now something that's between here and 3 would be, we're going to have to use something a bit more. How about 2.5? Oh no, I did something wrong. 2.5 store in X. Let's do that again. 2.5 stored in X, and then 2 times X times 2 times X squared minus 6 times X plus 3, 2.5. Wow, that's pretty interesting. So that's positive. Okay, so there's my sign diagram. So I can tell without drawing the function that from -1 it goes down, from x equals -1, whatever the value is at that point, it goes down, and then it goes up, and then it goes down, and then it goes up. Okay, so wherever the maximums are, they're going to be here. Wherever the minimums are, it's going to be where it went down and up. This one's a local minimum. This one's a local minimum. This one's a local maximum. And if it's going to be at this end, it came down from here, so there could be a maximum there or a maximum there. Okay? So I'm going to need to calculate what all of those points are. So we can see that there is a local minimum at x equals 0 and x equals 3 plus root 3 on 2 because it goes down, up, and down, up. And there is a local maximum at x equals 3 minus root 3 on 2 here because it goes up, down. And we could also have maximums and minimum. It goes down, up, down. So down, up, down, up. We could also have a maximum at 3. 3 is higher than this one, so it can't be a minimum. And the value at 0 is lower than the value at -1, so it can't be a minimum there. So you could also at the endpoints which is where x is equal to -1 and 3. Okay. So we'll actually figure them all out. So f of 0 is, let's find the original function, 0 squared, 0 minus 1, 0 minus 3, which is 0. F of 3 plus root 3 over 2. Well, we'll just sub that in and see what we get. 3 plus square root of 3 divided by 2. Store that in x. And we'll go x squared times x minus 1 times x minus 3. Negative 4.85. Okay, and so the global minimum can only happen at these local minimum places, and so it must be this one. Okay, and f of -1 is -1 squared, -1 minus 1, -1 minus 3. So that's 1 times minus 2 times minus 4, which is 8. F of 3 minus root 3 over 2. Minus root 3 divided by 2. Let's store that in x. And then we have x squared times x minus 1 times x minus 3, 0.348, and f of 3, 3 squared, 3 minus 1, 3 minus 3 is 0. Okay, so this one's the global maximum here. Because out of these three options, that's the highest. All right, so we have found, so just to sum that up, global max of 8 at x equals -1, global minimum of approximately 4.85, approximately at x equals 3 plus root 3 on 2. So it's tradition when someone asks you what the global maximum minimum is to tell them where it happens. Okay, so that's the idea of finding local maximums and minimums. First you find out where the turning points are, and then you can tell from whether it's positive or negative as to whether they're local maximums and minimums, which as I did here from the sign diagram. So I should probably actually tell the reader that I did that. From the sign diagram, they're the local minimums and local maximums. We could also have global maximum at the endpoints. And then we calculate the values at all those points, and we'll be able to pick which one is which. Okay. So that's great. That's for functions. How does this help me solve optimization problems in sort of, in inverted commas, or real-life problems? Well, if you can write your real-life problem as a function, write the thing that you want to find the maximum or minimum of as a function of something, then you should be able to use derivatives to solve it. So for problems in context, write the quantity you want to optimize. So optimize means make the best, right? It's short for optimal, which means the best. And the best might be maximum, it might be minimum, depending on what you're aiming for. Usually, you want to make the cost the smallest, because you want to cost the least, and you usually want to get the most stuff. So you usually want to make some other things the maximum. But sometimes having some quantities, it's best to have them small, in which case you want to minimize them. Some quantities, it's best to have them large, in which case you want to maximize them. So write the quantity you want to optimize as a function, and then find the global maximum and minimum. That's how we're going to do our problems in context. And it's really best to see with some examples. So, let me just have a look and find some. All right, this one is a classic, so I'm going to do it. So, an open rectangular box. Is made by cutting out equal from a rectangle of cardboard. Which has width 20 centimetres and length 30 centimetres. What is the maximum possible volume? The box can have. So this is a classic problem. It'll appear in pretty much any textbook that discusses optimization problems. And the idea is this. This is a rectangle of about the right size. And what we do is we cut out, or in my case, tear out, because I forgot I was going to be doing this and I forgot to bring my scissors, a square from each corner. Like that, and then I fold these up and I sticky tape them together to produce a box. Ta-da! Beautiful. And the idea is, what's the best volume we can get? So you can see already that's about the volume we have there, but if I changed these size of these cutouts, made them a bit bigger. Sorry, they're not squares anymore, but they're supposed to be. Then I would get a different sized box which would have a different volume. And if I cut out really big things, I might get a really tall, skinny box, and I reckon the volume might start to decrease. So somewhere in the middle, the volume would be the biggest it can be. I don't really know much about how that's going to work, so I'm going to give it a go. Okay, good. I had this terrible fear that I had used the piece of paper that I'd written the problem on to make my box. Okay, so if I'm going to do this, I'm going to have to create a function which describes what the volume is, because I want to find the maximum possible volume of the box. Along the way, it's probably a good idea to tell people how big the squares have to be cut out in order to do that, but I'll figure that out in a minute. And a good place to start would be to draw a diagram. And it's never a bad plan to tell someone there's a diagram, not least because if I was typing this on a computer, it would say diagram, and a person who was blind would be able to know that there is a picture there. Okay, so there's my rectangle, which is 20 centimetres this way and 30 centimetres this way. I mean, if it was a real A4 piece of paper, it would be 21 this way and 29.8 that way, but that's close enough. I wasn't trying to go for an exact thing. And then what I'm going to do is I'm going to cut out a corner from each one. Okay, and then they're going to be removed. And then I'm going to fold it up into a box. Okay. So when I fold this up, this edge here is going to be vertical. It's going to form the height of the box. This edge here is going to form one edge, and this one like the length of the box, and this is the width. And so I'll be able to figure out the volume of the box by joining them together. So just let me actually draw the resulting box. Like that. Good, that's a nice picture. And just for my own purposes, this edge ended up here, and this edge ended up here. And this edge, these two edges ended up here, like that, because they fold together. All right, and so I guess that's why it has to be a square that you cut out, although they're not going to join up properly. Okay, so I know that the volume will be different if I pick out different size squares. And so it would be a good idea for me to give a letter to the unknown size of the square that I cut out. And so I'm going to call this x here, that distance there. And all of these distances are the same. Okay. So now I'll write the text part of my story. So this is an x here, by the way. That's there. So I need to tell the reader what my letter X stands for, because the picture is not enough. I need to tell them in the written text. So I should say, let X be the side of the cut out squares in centimetres. I've been very precise. I've said it's X, and I said what it's measured in. Okay. And I'll probably say, shown in the diagram. Okay, so the width for the final box is going to be this yellow bit, which is going to be 30 centimetres, take 2 of these x's. So let me pop this in. The height of the final box is going to be x. The width of the final box is going to be 30 centimetres, take 2 lots of x. And, sorry, that's the length, I guess, because it's the longer edge. And the width of the final box is going to be 20, take 2x. Now, if that x is too big, I'm not going to be able to cut it out. The biggest that this x could possibly be would be to go all the way to the middle and you cut out stuff from both. And you won't actually be able to make a box then, but that's as far as it can go. So largest x is 20 divided by 2, which is 10. But no actual box at this x either. Okay, and the smallest x would be to not cut anything out at all, or we could cut a really teeny tiny one and make a really shallow box. Okay. Smallest x is 0, but again, no actual box. At this x either. And so therefore, I can say that so 0 is less than x, which is less than 10. So it's not actually allowed to be either of those ends. That's going to become important when we do the working. Okay, and so we should probably, I probably should have done this in a little different order. I should probably have figured out the volume here, but whatever. So from this information here, so now let V be the volume. Because if I'm going to use a letter, I have to tell them what it is, and giving a letter to that is going to make it easier for me to do my calculations. Let V be the volume of the final box, and then V is going to be the height times the length times the width. Okay. You'll notice I didn't say L, W, and H because the reader doesn't know what L, W, and H are, but they do know what the words height, length, and width mean. So it's just quicker to just say them in words. Okay, so we have a formula for what the volume is going to be, and we have a range of, a domain technically, of possible x's that we're allowed to have. The word domain means the x's you're allowed to use in a function. So I have written v as a function of x, and now I know that if I want to find the maximum or minimum value that a function takes, I need to differentiate it and see where the turning points are. Okay. So dv on dx. I might even put a heading here. Find the turning points. dv on dx is Okay, well I guess I can use the product rule like I did last time. I could expand it out first. That might be more productive, I think. Don't really know actually. So they're both going to be about the same amount of work. I feel the derivative is going to be easier for me if I don't use the product rule, so I'll just expand this out first. So sorry about that, I'm not going to find the turning points yet. I'm just going to do some algebra first. So I'll do this bit first. So 30 times 20 is 600. 30 times 2x is 60x. 2x, oh, that'll be a minus 60x though. 2x times 20 is minus 40x. And minus 2 times minus 2 is 4, and the x times x is x squared. So that's x times 600 minus 100x plus 4x squared. And so I've got 600x minus 100x squared plus 4x cubed. Now I'll find the turning points. So dv on dx would be 600 minus 100 times 2x plus 4 times 3x squared, which is 600 minus 200 plus x plus 12x squared. Okay, cool. And we need to find when that's 0 so that we can figure out when the function's increasing and decreasing so that we can figure out where the turning points are. So dv on dx equals 0. So I'm just going to write my function the other way around, if that's okay. Okay. Well, I can see 4 goes into all of those, so I might as well do that now. And divide by 4. Don't know if that's much better. Really distressed that the middle there doesn't divide by 3. That would be kind of cool. Let me just check that I've done my working right. 600, 60, 40. No, really is 100, the 60 and the 40. Okay, well, I can't think of anything other than the quadratic formula to do this, so that's what I'm going to do. I guess the 3 just doesn't go into that. That's going to be annoying. So we've got that x is equal to minus b plus or minus the square root of b squared minus 4 times a times c over 2a. Okay, so 50 squared is 2500. Yep, that's going to be okay. I mean, there is a 50 in here. I could pull that out. That's not too bad. Let's try that. 50 plus or minus 50 outside of 50 minus 4 times 3 times 3. Because the 150 is 3 times 50, and the 50 squared. Well, 50 is 2 times 25. 4 times 9 is 36, so 50 minus 36 would be 24. Calculator's a 4. Oh, 14. Yeah, sorry. No, that's not nearly as nice as I would have liked. So it's not going to be pretty, is it? Okay. 50 plus or minus, well, that can come out. That 14 is 2 times 7, so that can come out. All right. I guess I can divide by 2. That's as simple as it was going to get. I was hoping for something prettier, but that's all right. Best to figure it out approximately. It is an applied problem anyway, so if I really wanted to do this, I actually couldn't find the volume. I couldn't find an x to be exactly 25 plus or minus 5 root 7 over 3. So I probably should have right at the beginning just calculated what it is. So let's see, what have we got? We've got 25, going to need some brackets, 25 minus 5 times root 7 over 3 is 3.92. Do it with a plus, 12.74. Okay. Well, this one doesn't count because my x's had to be less than 10. So this not valid. I really should actually be more specific with it. But x is less than 10, so x equals 12.74 is not valid. Okay. And so therefore we have this sign diagram. Okay, so I need a sign diagram. I had to pause the video because someone came in to say hello to me. So I think that this dv on dx has just appeared without me writing it. Sorry about that. So sign diagram for dv on dx. Now let's see. The x's were only allowed to be between 0 and 10. And it wasn't actually allowed to be 0, and it wasn't actually allowed to be 10. Okay, and the only place where the dv on dx is 0 in between is 3.92, and it is actually equal to 0 at that spot. So these are the x's, and this is going to be what the dv on dx is. Okay, so I just need to figure out whether it's positive or negative in these ones. And look, if there is a maximum, it's going to have to be here, right? Because if this was a local minimum, it would increase up to here to 0, and it would never get bigger. And I know there has to be a maximum because based on my calculations with the piece of my rough idea with the box with paper, it sort of got bigger and then smaller. So let's see if the mathematical theory connects with that. So when x is some number in here, let's say 1, then dv on dx is 600 minus 200 times 1 plus 12 times 1 squared. Which is positive. And when x is, say, some number in here, let's say 5, dv on dx is 600 minus 200 times 5 plus 12 times 5 squared, which is 600, well, I've got a calculator. That's 1,000. So 600 minus 1,000 would be minus 400. 12 times 5 would be 60. Times another 5 would be 480. It's going to still be negative. It's going to be minus 20, I think. So let's have a look. It was 600. Minus 100. Oh, well. Okay, so my function is increasing up to this point and decreasing after that point. It's a local maximum, and since it's the only local maximum, and since these endpoints here can only be minimums because we decrease from down to this point and increase from that point, that must be where it is. So I might just pop that reasoning in. So since, and these points don't even exist anyway. So the only place where there can possibly be a maximum is at a turning point or at one of the endpoints, and there are no endpoints, and so it can only be at a turning point. So x equals 3.92 is a turning point, a local maximum there are no endpoints, so therefore global maximum at x equals 3.92. Okay, so that means that the volume, when x does equal 3.92, v equals, now where's the original formula I had for v? Here it is. 3.92, 30 minus 2 times 3.92 times 20 minus 2 times 3.92, which is, and that's exactly what calculators are for, 3.92 times 30 minus 2 times 3.92 times 20 minus 2 times 3.92. 1056.3 centimetres cubed. So I guess we should sum this all up with a sentence so that whoever's reading it knows we're done and can actually find the answer. So the maximum volume is 1056.3 centimetres cubed, so just over a litre. A litre would be 1,000. When the cutout squares have sides 3.92 centimetres. Okay, beautiful. And that's how you do it. And the whole point of it is to not draw the graph, but to use the reasoning that we have to figure it out without having to draw the graph. So I should do one more example. Okay. So let's see. Okay. So a sector of a circle just a second, it's going to take me a while to write this properly. A sector is cut from a circle of radius, let's say 10 centimetres. And rolled to form a cone. What angle should be chosen for the sector to maximize the volume of the cone? It's another maximum one, I'm sorry. If I have time, I'll try and do a minimum one, but I'm not sure I will have time. Okay. All right, so this one specifically asked me about an angle and about the maximum value of the cone. So it seems to me that I should use as my variable the angle and use as my function the volume of the cone. But I'm going to need to know what a sector is, and I'm really going to need to know how to find the volume of a cone. I reckon that's going to be useful. So let's just do a diagram. So let's see. So that's my circle of radius 10. And a sector is like a pie slice. That's my sector there. And we should give a name to this angle. I could call it x. That doesn't seem too bad. It's traditional to call the angle theta though, so let's call it theta. Okay. And then what we do is we turn that into a cone, like that. All right. So if I'm going to need to find the volume of that cone eventually, and to find the volume of a cone I'm going to need to know its radius and its height. Okay, cool. So since those are the things I'm going to need, so this is a sector cone. I should tell the reader what they are. Let theta be the sector angle. Let R cone. Let H be the height of the cone. And let V be the volume of the cone. So let's see. Whoops. All right. Well, I know, so I can figure out some relationships between these things. So I know that the area of a sector is a fraction of the circle, and I need to figure out what fraction of the circle it is. And I guess that the angle would be an angle out of 360 degrees. Let's do our angle in degrees. As a mathematician, I should probably do it in radians, but degrees will make it easier if I'm doing an applied problem to actually measure it, because I don't have protractors that measure in radians. Okay, so I know that the fraction of a circle will be theta out of 360 degrees. Okay, and the area of the circle would be pi times the radius of the circle squared, which would be 100 pi. And so therefore the area, I don't know if I need the area of the sector, I'm sorry. That's probably not necessary, but I'm going to write it down anyway. Equals pi times, well, it's this fraction times 100 pi, which is whatever it is. I don't think I actually need that though. I guess I really want to figure out what R is in terms of theta and what H is in terms of theta. Okay, but just a second. If this length here becomes this length here, so the outer edge sector becomes the circumference of the cone's base. Okay. So the outer edge of the sector would be theta on 360 times the circumference of the original circle. Okay, so I should actually say circumference of the original circle would be 2 times pi times the radius, which is 20 pi. And the outer edge of the sector will be this fraction times the 20 pi, which will be pi times theta on 18. Okay. So I didn't need the area of the sector. I should probably remove that from the working because it's probably just going to confuse the person who's reading it. Okay. And so therefore we also know that the circumference of the cone's base is going to be 2 pi times r. And so therefore, 2 pi r is equal to pi theta on 18. Okay, so that means that r is going to be pi theta. Oh, well, they've both got a pi. So 2r is theta on 18, which means that r is theta on 36. Okay, so we've now written the radius of the cone in terms of theta. That's great. We're going to need the height if we want to find the area of the cone. So let's see. Oh, this is 10 here, isn't it? Because this came from gluing these two edges together. Oh, okay. So if it's 10 here, it's that radius out here and that height here. I can actually calculate that. I'm just going to draw a new diagram. That's the radius from this point to the edge. That's the height there. And we know this is 10. So from Pythagoras' theorem, we can say that I like saying from Pythagoras. It's like a gift from the past. From Pythagoras, using the edge of the cone, we get that r squared plus h squared should be 10 squared. So r squared. Now what are we trying to figure out? We want to figure out everything in terms of theta. Okay? Because the point was to figure out what the angle was that produced the correct volume. Yeah, that's the story. We began with this angle. So we should figure out what h is in terms of theta. We know what r is in terms of theta. That's theta on 36 squared plus h squared is 100. Okay. So h squared is 100 minus theta on 36 squared. So h must be the square root of 100 minus theta on 36 squared. Okay, so now I've got the r in terms of theta and the h in terms of theta. It should be possible to figure out the volume from this r and h. So let's see. Now the volume of a cone is 1/3 times the area of the base, which is pi r squared because it's a circle, times the height. Okay. So that's 1/3 times theta on 36 times pi times theta on 36 squared, because that's the third, that's the pi. R squared was theta on 36 squared, and h is this. Okay, that's my formula not pretty. I might just do a little bit of work here. So pi theta squared on 3 times 36 squared. I don't think there's any reason for me to calculate what that is. And I might just write this as... Do you know what? I'm just going to leave it. But I am going to write this as a power of a half, because that's going to be easier. I also remembered I gave a letter to that. Okay. So pi on 3 theta on 36 squared times 100 minus theta on 36 squared to the half. Okay, let's see. So what we want to do is we want to find the turning points. Okay? I should probably go right back to the beginning and go, well, the theta would go anywhere from 0 to 360 degrees, I guess. So theta will go from 360. And I guess if it's 360, there won't be a cone, it'll just be a circle, but I guess the volume is just going to be 0. And if it's 0, there definitely won't be a cone at all. So I think we're not going to include these ends. So no cone when theta equals 0 and 360. Okay. Cool. So we know what V is, we know the range of thetas, so we really should be trying to find the turning points because that's when my function will be at its greatest. So we're going to find and the only way to find turning point, well not the only way, but one way, since I have a function, to find turning points is to find when the function's increasing and decreasing, in which case I'm going to need to find the derivative. So let's see, dv on d theta. Now that pi on, I can see that my v is made of 2 pieces, and I have a piece here and a piece here that are multiplied together, and so I can do that. So the derivative of this part will be pi on 3 is multiplied on, so it will still be there. I'll have 2 lots of theta on 36 to the 1, and then because of the chain rule I'll have to multiply by the derivative of this, and the on 36 will still be there because it's a constant divided, and that'll be 1, and then we'll keep this bit. It's looking pretty complicated, but let's hope it doesn't turn out too bad. And then we'll keep this first bit, and now we'll differentiate this bit, so we'll get a half times all of this to the minus a half. And then we'll have to multiply by the derivative of the inside, which is minus 2 theta on 36 to the 1. And then because the derivative of that would be 1 on 36, we already did that. Okay. Well, great. I can see a theta on 36 in everything there, and there's a pi on 3 in both parts, and there's a 1 on 36 in both parts, and there's a 2 in both parts. So let's see, we have a pi on 3 times 2, that's this bit, that's the 2. We have a 1 on 36, and we have a theta on 36 as well. And what's left behind here is we have 100 minus theta on 36 squared to the half. And what's left behind in this bit is a minus half theta on 36 squared times 100 minus theta on 36 to the minus a half. Okay, right. So we want to solve for when this is 0. Because there'll be there will be a 0 there, right? So we want to know when it's 0 so that we can know when it crosses over from positive to negative. So let's see. Well, this bit's not going to make a difference to it being 0. We know that theta can't be 0, so we don't have to worry about that. So that just leaves this bit, i.e. so half of theta on 36 squared since theta is not 0. Okay, beautiful. So now we have to solve this. This does not look fun, people. I'm not liking the idea of doing this, but I guess I can move this over there. And can I put my square roots back? I'm just going to put them back because this power of a half thing is freaking me out. It's a minus a half, isn't it? Good thing I noticed that went missing there. So actually, before I do anything, I think the best thing to do is probably to multiply by this, because that'll clear it off the bottom. So if we multiply by this here, we'll get 100 minus theta on 36 squared, because it'll be square root times square root. And then this will go away. That was a squared, wasn't it? Yep, okay. All right. So I have 100 minus theta on 36 squared minus half of theta, so that's 3 halves. Okay, that's good. Good, there's only one theta. We can solve that. If we move this 100 over there, and then we can make them both positive, and we can clear that 2/3 by multiplying by 2 and dividing by 3. Okay. And then we can square root it. And then we can multiply by 36. All right, so that's an answer, and we have one answer, just one, because technically we could get a plus or minus here when we did that square root, but we know that theta cannot be negative. Okay, so let's just see what that works out to be. What have we got? We've got 36 times the square root of 2/3 times 100. 293. That's a pretty big angle. I would have expected it to be not that. That's just a cotton picking minute. Really should have brought scissors, shouldn't I? Well, that's 180. That's 270. We need another 20 degrees or so. So this seems to be telling me that cone has the biggest volume, just there. Well, it does seem to be getting smaller if I go that way. Definitely gets smaller if I go that way because it flattens out. Well, maybe it is correct. Okay. just going to check my working. I'm just feeling uncomfortable, so just go back to this bit. Do my derivative again. The pi on 3, 2 times theta on 36 to the 1 times 1 on 36. Interesting. And then I've kept that bit, and then I keep this bit, and I've got a half of that to the minus a half, and then I've got minus this, the 2 comes down, pi, theta on 36 to the 1, 1 on 36. Yeah, that seems to work. And I pulled out all of these things. No, not that. And so that leaves behind that thing, and minus a half of theta on 36 squared times that to the minus a half. And I did copy that correctly to the next line. And then I turn them correctly into square roots. Multiply everything by that square root. My squares are carrying correctly. So 100 minus this, minus another half. Well, that's 2 on 2, so that's 3 on 2, yep. Minus 100, 2/3. All right, seems all right. I did do it in the calculator correctly. Okay, that's what it seems to be. And so I can make a sign diagram. dV on d theta. Now it went from 0 to 360, and then I've got my turning point here at 293.9. That's theta down there, and I should just test the values. So when theta is, well, we can pick anything. Maybe there's something nice and convenient. What about 36? Then that means that dV on dx is back here. Stuff, I'm going to say C times 100 minus 1 squared, because it's theta on 36, minus a half times 1 squared, 100 minus 1 to the minus a half. Okay, so that's the square root of 99 minus a half, 1 over 2 times the square root of 99, and that's a really small number, so this is going to be positive. Okay, that's good, as it should be. And when theta is something bigger than 36, I could technically pick 360, but it's not actually in the zone, so I won't. But what if I picked 360? What if my theta was like 360 minus 36? Because then theta on 36 is like 10 minus 1, which is 9. So then V on d theta is going to be some constant times 100 minus 9 squared to the half, minus a half of 9 squared times 100 minus 9 squared to the minus a half. So we get C times 100 minus, so the square root of 100 minus 81, which will be 19, minus 1, so 81 over 2, 19, square root of 19 minus 81 divided by 2 times square root of 19, which is negative, as we hoped. So my function increases to here and decreases there, and so therefore it must be a maximum at that point. So let's see, we found our turning points. So there's a turning point at theta equals 239.9, 293.9, which is a local maximum. There are no endpoints, and so therefore as a global max at theta equals 293.9 degrees. And when that happens, we get V is, where's my formula for the volume? There. Pi on 3 times 293.9 over 36. 100 minus 293.9 over 36. That's squared, and that's to the half. Okay. Now, I just really should figure out what that number is exactly, rather than using the rounded off version. So I'm just going to go back to here and go, I'm just going to put it as an x, hey? So we had 36 times the square root of 2/3 times 100. And we'll store that under x. And then we'll calculate this thing. Where's my pi on this calculator? Don't use a calculator very often. Oh, there it is. There's a whole button for it. It's right there. Okay, pi divided by 3 times x divided by 36 squared. Oh, that's a squared. Just a second. Squared times the square root of 100 minus x divided by 36 squared, which is 403.1 centimetres cubed. Okay. So, the maximum volume is 403.1 centimetres cubed. Occurs when the sector angle is 293.9 degrees approximately. All right. Okay. So I don't have time to do another full example, but I could do a couple of what-ifs in the next 5 minutes. Just let me have a quick look at what happened here. You'll notice that there were two parts to both of these questions that we did. The first part was the part where I explained how I got the formula. And this one was quite complicated, and I began by drawing a diagram and saying what my letters stand for, calculating various bits and pieces so that I could eventually combine it into one big formula involving just that, that letter. And then I found the turning points by differentiating and doing a sign diagram, and then I would know where the turning points are. And then I summarise it at the end with a sentence because that's exactly what I would say. So in this problem, I did a diagram as well, and then I told the reader what the different bits were. And this time I didn't give letters to the missing pieces. I just told the reader in words what they were, and then I calculated a formula so that I could find the turning points, which I did by differentiating, setting it equal to 0 and drawing a sign diagram. By the same reasoning. Okay, so just some thoughts about some things that might happen here in the 3 minutes I have left. What if, just some what ifs. What if the sign diagram had said dy and dx, and this is x? And what if it had been like that? Well, in that case, I would have a minimum here, maximum here goes up and down, and it continues going down. And so there would just be a maximum. So let's just say this is at 3 and 5. Then at x equals 3, we have a local max. And then there's no minimum, because it goes on forever both ways. So this is not a turning point, so it doesn't count. So that's x equals 5. There's no turning point there. So therefore, at x equals 3, there's a global max. Global maximum. And I just wanted to point out that it's possible for that sort of thing to happen. Thanks for listening. You could ask your own, I know it's not quite a couple of minutes to go. You could ask your own what-if questions in similar ways. Yeah, that would be a useful way to try and figure out how things are doing what they're doing. So what if my sign diagram had been like this? Like that. And then I would know that there's a global maximum. So it goes up and then down. So there's a maximum here, and the minimum could happen at one of these places. So at x equals 1, and that's an endpoint, and it could be a minimum because it goes up from there. At x equals 2, there's no turning point. At x equals 3, it's a local max because it goes up and then down. And at x equals 4, it's an endpoint, but it could be a minimum. And so then if I wanted to find the minimum, I would just sub those two in. And if I wanted to find the maximum, it would be that one. It's a global maximum. And I would have to compare these two to figure out which one it was. Thank you very much this time.